So, what did Kepler say that was so revolutionary? What did he come up with? He came up with what we now call Kepler's laws of planetary motion. After a lot of policing, Kepler reduced Tycho's data to 3 laws. And I put the laws in quotation marks here because they're not really explanations so much as descriptions. They're a list of the way the planets are actually observed to move. And therefore, anybody who's going to try and explain what's going on will have to meet each of these 3 laws. The model of dynamics that explains the solar system will have to include each of these features. And that turns out to be quite the gatekeeper. So law number 1, each planet moves in an ellipse, not in a circle, and where one focus of the ellipse is occupied by the sun, and thus is shared by all orbits. The other focus has no physical significance. So that's the first thing. He says the reason that nobody could make it work with perfect circles going around the Earth at perfect speed is because they just don't. They move along elliptical paths no matter how much people want them to be circular paths. It's kind of bizarre, but for about 2,000 years, people had basically assumed that the orbits would have to be circular. They looked relatively circular, and circles were quote-unquote perfect. And Kepler said, I don't care. The actual data says they're moving in elliptical orbits, close to circles, but not circular. Law number 2. Each planet moves with a varying velocity, such that the planet is moving fastest when it's closest to the sun and slowest when it's further away. Moreover, planets that are closer to the sun will move faster than planets that are not, that are further out. So again, he says the other thing about the Greeks was that they wanted things to move at constant speed because that was honestly the only speed they could handle, and they thought, again, it was perfect. And he says, too bad for that the planets do not move in with a constant velocity, but instead have a varying speed throughout their orbit. And then the third law from Kepler says there's a relationship between the period t of the orbit and its semi-major axis r, which is sort of like the radius for ellipses. The semi-major axis often acts like what we would think a radius does for a circle. And in fact, in a circle, which is one form of ellipse, the semi-major axis is the radius. The period t, then, is the length of time it takes to complete one exact orbit. The relationship exists, but it's a bit bizarre, that r cubed over t squared is a constant, where that constant is the same for every planet. He didn't say where the constant came from. He had a value, but he didn't know what it meant. But he says, but every planet obeys that r cubed over t squared is the same. The ellipse is a geometric shape that looks kind of like a squashed circle. It's one member of a family of curves called conic sections. They're called that because if you take a right circular cone and you slice it different ways, you get that shape. Like if you slice it across like this and looked from above, you would get a circle. And if you sliced it at an angle and looked from above, you'd get the ellipse, and so on. Conic sections have a formula that's the same. So in analytic geometry, they all have a formula that fits ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And for different values of those letters, you get all the different conic sections. So there's a lot going on here that they're really the same kind of shape. The ellipse is the set of points such that the sum of the distance from any 2 points, each called a focus, is the same. So here we have, if these 2 green dots are our focus, then for this ellipse, the sum of these 2 distances is always the same, even if we go to a different point. So like that and like that, we would get the same distance, or if we went there and there, we get the same distance. The squashedness of an ellipse is something called its eccentricity, denoted by the Greek letter epsilon, where epsilon equals 0 would be a circle, and epsilon 1 is a parabola. Everything between 0 and 1 would be a standard ellipse. For objects in the solar system, the eccentricity is very close to 0. The most extreme is Mars, and it's something like 0.002. So that's why people thought it was circular. They're very, very close to circles. But Tycho's data was good enough that Kepler could say they definitively are not circles. The first law was a little odd but acceptable. It relates the motion of the planets to geometry, not as simple as a circle, but still pretty simply. Kepler gave the second law in a slightly different fashion. He said that if you connected the planet to the sun with an imaginary line, that line would sweep out equal areas in equal times. For instance, each of these shaded areas are the same because the time between them being generated is the same. If you look at that. That ends up being the same, equivalent to saying the planet speeds up as it nears the sun. You can see that again, or at least gets slower as it's further away from the sun. This thing is true. It was odd as well, but it isn't all that alien. It's weird, but not crazy weird. But the third law, oh boy, was that one a doozy. You could come up with a lot of different possible force laws for what keeps planets moving around the sun, and it's fairly easy to find some that give rise to the first and second law. In modern parlance, we would know these require only the force be central and be distance dependent. The first law is basically that it's a central law, and the second one is basically that angular momentum is conserved. But the precise and aggressive nature of the third law broke many theories. Descartes, Hooke, a whole bunch of people had different theories that they were pushing forward, and they just could not get past the third law. The third law kept them aside. Over here on the side, we have the best data from NASA from, I guess, a couple years ago now, which is the distance of each planet from the sun versus its period, and we're measured in terms of the AU, which is 1 astronomical unit, the distance of the Earth to the sun, and 1 year, which is the time it takes the Earth to go around once. So the Earth, of course, would be, you can see that blue dot here at 1,1. And we can see we go all the way out here. This is Mars, Jupiter, Saturn, Uranus, Neptune, and even Pluto, even though we know Pluto is not considered a full-on planet anymore, but it was data that we can put onto this chart. And we see this kind of weird curve. If instead we plot the period squared versus the distance cubed, then the inner solar system looks up pretty nicely. We have Mercury, Venus, Earth, and Mars. We see that of the ones that vary the most, it's Mars, which is the least close to a circle. And that's because I'm treating this as if it were a radius, but it should be, right, that's the distances I had. But really, it's the mean radius, and I need to have the semi-major axis, and Mars is the furthest off because it's the least circular. So it's not surprising that although it seems to fit the line, it does miss just a little bit. This is not terribly impressive. 4 data points hitting a line. That's, neat, but not particularly impressive. But it's interesting if you take a step further out. Here we have the inner solar system, all the planets I've already named. So Mercury, Venus, the Earth, and Mars, all in that little dot because Jupiter is so far away, and when we cube it, it gets even more crazy and so on. But here's Jupiter and Saturn, and it's the same line. So you have to believe me or not, but this in Desmos, I did not refit the line. I just re-zoomed out from my original inner solar system fit. And so this line extended over unimaginably greater distances still hits. And this is where Kepler was. Kepler's like, I know all of these planets, and look at how crazy well they fit. He didn't say it quite that way, but we can believe that this law seems to mean something, even though it's a little strange, being t squared proportional to r cubed. But it kind of gets better. Planets that Kepler didn't know about. They're invisible to the naked eye, and Kepler was a pre-telescope person. But in the 1700s and then the 1800s and then the early 1900s, we discovered other planets, Uranus, Neptune, and at least for a little while, Pluto. And when we plot their data on the same extended line, they hit straight on. So we're getting the sense here that this is actually quite impressive, that this is not a fluke, but is actually really a law of nature somehow. Notice Kepler doesn't explain it. He just says this is the data, and that's what we're sharing here with modern values. It will take someone else to come along and say, hey, why would that be? Let's try and explain that. Kepler gave up on that. At some point, almost vengefully, he said, I don't know, and you don't either, but maybe somebody in the future will.